How's it going, everybody? And in this video we are going to be learning about machine learning. And so this is definitely some subject that I think is personally for me pretty intimidating, but I've been spending some time these past few days trying to learn it, and I'm going to share with you guys what I've been learning. And I will say, I think the best way to get started on this, whether you're on a Mac or a PC or a Linux or whatever, is to take advantage of the online Python notebooks that Google provides, and it really helps with a lot of the setup stuff because I was trying to do this in PyCharm and I was running into tons of issues on my local IDE trying to get the right packages and versioning. And if you are trying to do this on your local computer, the biggest issues that I was running into was the fact that I was originally running a 32-bit version of Python, so you need to be having a 64-bit version of Python to make this work. And then in addition to that, there's just a ton of versioning in TensorFlow that's happened over time that makes it pretty hard to always find like up-to-date relevant examples. But if you do a little bit more digging, you will find excellent resources on GitHub that the TensorFlow authors have created, and so I'm providing a link to that. But this stuff is fantastic, and this is what's really saved the day for me. And here's the file right here, and I'll provide a link to this in the description. But these guys are great. They literally walk you through every step, and they explain why you're doing what you're doing. So I'll just add some context to what is already there, and I want to give them full credit for all this stuff. But yeah, so before I actually start running any of these code snippets or code blocks, the very first thing that I want to talk about is just the theory behind machine learning, and we'll get started with that. So basically, without looking at any code, the whole reason people even care about machine learning is that it allows people to use data to answer questions. And how is that different from conventional programming is that instead of us trying to pick through data sets and define our own trend lines and work out whether or not we think that's the line of best fit, we outsource that, or we script that whole process to a computer. So there's tons of different ways of modeling your data, and so what we basically do when we are using machine learning is that we say, we're just going to let the computer tell us what it thinks the best data is, and we have ways of training our models to come up with some things that are more accurate. And so another very high level just kind of vocab with machine learning is that you have features and labels and models. And so what are features? So features are inputs into your model, and your model will look at all these features and it tries to determine, based on these features, what should I label this as? So what label is this? And so the kind of hello world example of machine learning is these flowers, the iris family of flowers right here. And so why people like it so much is that there are a bunch of different length dimensions that you can measure on these flowers, and by measuring all these different lengths, it gives us some numerical data to look at. And so these three different species of flowers, even though they might visually kind of look similar, have different lengths. And so we can look at how this will help us determine, based on, if I just encountered one of these three species of flowers in a field and I didn't know what it was, I can measure these things and then plug this into a model, and then that model would tell me with some degree of confidence which of these flowers it has to be. And so that's the power. It's the ability to make predictions on data that you haven't seen before. So without knowing a priori, oh, this is this specific, species A of this flower, I don't care. I can just throw this into my model. I can give you a confidence interval, and my computer does all the rest for me. It does all that hard work of trying to figure out, what makes species A different from species B, different from species C. We're letting the computer do all that for us. So it's pretty cool. Now I will start walking through this, and I'll try to be very clear on what's happening. I'll show you guys visuals. But basically the first thing you do, and I know one of the hard things for getting started with this is just like, what data do I even use? So the very first thing we're executing here in this first snippet after we've imported our libraries is the following. So Google provides this training data set in a CSV format for our iris flowers, and we're basically just saving this to the disk that we have on our little virtual machine right now. So just run this guy, And I've downloaded this to my own computer just so I can show you guys like what is this file really. And so this is what it looks like. It's a little weird when you first look at it because like this first row is just, you know, so basically what 120 refers to is that we have 120 observations. And specifically what that means is, you know, if we just look at the end of this Excel, we have 120 rows. So basically what this is just telling us is that in our training data set, we have 140 different observations to look at. So 140 different flowers we measured. And so we know that, you know, for this particular flower, so that's what 120 refers to. The 4 refers to the number of features that we have. So 1, 2, 3, 4. And then this final column right here, column E, is referring to the species of flower. And so we have Setosa, versicolor, and virginica. And so that's 0, 1, or 2. So it's saying that for basically in row 2 right now, with these specific dimensions, these 4 inputs for these features, this was a virginica flower. And then we just, you know, keep going down the line with all this other stuff to see that, you know, this line with these particular dimensions, this flower had to be species versicolor. And so we have 120 of these different points to look at, and this is what we're going to be using to actually build our initial model. So this is the training data set that you'll be using. And so basically the only thing that's really happening here is we've downloaded this CSV file and we are just being specific about it. I print out this little statement to say where it's saved it. You don't need to do that, but I'll provide a link to this too so you guys can walk through this just like I am. And then the next thing we're going to do here is we're just defining the different names of each feature here. So literally just saying column A right here corresponds to sepal length, column B corresponds to sepal width, column C is petal length, column D is petal width. So we're just saying exactly what we have here. And then the label name, so that was, you know, that is the last column in this CSV file, and that's where we're saying what it is. So we're just telling Python and TensorFlow how to interpret this CSV file that we're putting in. So if you're going to do this with some different data set, this is how you're going to want to do it. We're just printing that out, so pretty straightforward stuff. Also, knowing exactly which version of TensorFlow you're on is really important. I'm using 2.7, but they are constantly versioning this thing, so just, you know, if you want to replicate this exactly, try to stay on TensorFlow 2.7 if you have a chance. And so that's that. And then in this next part right here, this is where we're actually going to start defining the TensorFlow objects that will contain all this data that we're about to pass into it. So we've saved that CSV file. So that's what this first argument or parameter is. And then we're defining a batch size. Batch size is going to be dynamic. For whatever reason, the author is setting that to be a constant value in this case. And the cool thing about these notebooks is that you can like run this thing, and if you get an error, you can like try different, you know, values here. So that's what they're using. And these other things are pretty easy to see. They're literally just defining the columns and the labels and epochs. And so that's how we do that bit. And now we're just going to be printing out the features that we have here. And it's literally just getting the data structures right in terms of how does TensorFlow want to see all this data that we've just given it for our training data set. And then this is us just plotting what we see. And so it's pretty cool. They colored these things. So you can see how by looking at only 2 of these inputs, the sepal length and the petal length, we're able to see some distinctions between the 3 species of flowers that we're looking at. And we had 2 other features to look at, so they're not being visualized in this, but you know, we can add a 3rd dimension to this thing. We can't do a 4th dimension visually, unfortunately, but basically, you know, we can start seeing how you know, there is some nice separation in this thing. Another thing I want to make note of that is important, and I'm sorry this is going to be a long video, but basically your training data set is very important for machine learning. The reason is that if you look at this picture, like one of the things to note is that we have relatively equal data points for each one of our 3 species of flowers. And so implicitly what we're saying by having equal numbers of observations in our training data set for each of the 3 species is that when we're making predictions, we're assuming that that we're going to be equally likely to see any 3 species of flowers present. And so the reason why it's important to make note of this assumption is that if most flowers were going to be of species C, for instance, and our data set is, or our training data set's mostly focused on species A and B, then it's going to be a pretty poor predictor of species C flowers. So you just want to make sure that your training data set is an accurate representation of what you expect to see in the real world. And that's where statistics comes into this, and random sampling and all that stuff. But that's a very important note to make here, is because, you know, machine learning is a super powerful tool, but if you give it the wrong training data set, you're just going to end up getting garbage out, because you're failing to accurately give your model a good piece of information to train on. So that's an important bit to make. Now what we're going to do is we're going to define a function here, and this is basically just, again, rearranging the data that we have in such a way that TensorFlow can make a training data set object out of this thing. And so we're just running this thing, and hopefully you guys don't get any errors. If you do get errors, I recommend starting from the top and just kind of iterating through this entire thing, because I know it can get frustrating sometimes, but just stick to everything that's here. It should work as of today. And now we're going to define an actual model. Okay, and now we're going to make some predictions with this model. And what you're going to see here is that, note how epoch was set to 1 on one of these lines. Sorry, on one of these lines. Epoch was only set to 1, so we only did like 1 cycle of training really for our initial first pass here. And so like what happens when you initialize your model, which is what we just did, is we've assigned basically random weighting to everything. So it's going to be pretty dumb. It's like someone who's never driven a car before getting into a car and being told to drive. They're not going to know how to drive. They're going to keep hitting the brake pedal and wondering why the car doesn't move forward, is because we've initialized our model. So it's lacking refinement right now, is the nicest way I can put this. Another thing I want to make note of is, you know, we've just defined this model, but what is this model? Because you can have many different types of models. And so what we're doing here is we're making this thing called a dense neural network. Dense means that you have, and this is a part where it's good to have a picture. Basically what dense refers to is the fact that you have each layer of your neurons within your hidden layers is connected to every previous layer's neuron. And so essentially what you have is your input layer. So this is where you feed in those features. And so, you know, some parameter for all these dimensions. And then you have you're defining. So let me just make that. Basically what you can see right here is that there's going to be 10 of those neurons in each one of these layers. These are all parameters that the authors of this article and TensorFlow have decided a priori. And so a lot of these parameters are things that take trial and error to fully elucidate. But for the sake of this hello world example, we're going to stick to what they've already found for us. So like if you're having really inaccurate models, this is one of these important points where it's like maybe you want to change how many layers you have in your neural network, or change the number of neurons you have in each layer. These are where you would actually make those fine-tuning adjustments in this process. And so that's really what this thing is showing us, is that we've got 2 layers, 2 hidden layers here, and then that final output layer. And the reason why there's a 3 here is because we had 3 species of flowers that we're trying to guess. It could be species A, B, or C, and so that's what our output layer is going to have to be. And then our input layer was looking at those 4 features that came in that we have no idea what they could be for. And so this is the secret sauce that's going on in your machine learning models. And I will say I'm pretty impressed by how quickly this all runs in the cloud. So not even on my local machine, we are doing machine learning, and it's pretty cool. And I really appreciate what Google is doing for everyone here. But yeah, so you've got this model. We've initialized this model. It's dumb in a sense because it has no idea what anything is, but that's to be expected. And we're just proving that right here by seeing how poorly it predicts everything. So like what we did in this particular code block is we gave it some data and our model just said everything was 0 because it doesn't know better. And what we're seeing is that it was right sometimes, like, but a lot of the other times it was wrong. And so this is like trying to teach a kid math, and they don't know anything, and so they just answered C on everything because the right answer is always C. And so that's basically what we're seeing here with our little model is it still has to be learned. We have to teach it before it can be expected to be good at predicting stuff or answering questions. So that's the part now where we're going to get into the training part of this. And so what we do is, I know this is some more code, but if you just run it, I'll talk about the theory. So basically what's happening here is that we are defining this thing called loss. And so loss is analogous to the number of points you missed on your math test. So basically it's like how poorly did you do on your math test, if you're teaching a kid how to do math, the loss is how poorly that kid did on their math test. And so the goal here is to minimize loss. And so we've defined a function in Python to take our model that we are training and to return how poorly this thing has done on its test. And so basically there's some optimization going on in the background here, but the gist of this thing is that right now it's not great, but as we teach it, the loss will improve. Like as you teach a kid how to solve algebra equations, they should be doing better on their algebra test. So hopefully this makes intuitive sense. We are defining another function here, and so we're just running this, and we're going to run this guy again. And so the cool thing that you see with this that's going on these lines is how we've got our model, we're teaching it, we are, and we've just done one loop of iteration. And so what this means is initially its loss was 1.77, and after we trained it the first time, its loss is now 1.51. So it's showing improvement in terms of the training. So like we had this kid, we sent them off to a math tutor for one day. The kid came back, they took that same math test, they took a different math test, but still algebra, and now they've missed slightly fewer points on their exam than they did previously. So that's what's going on right here, is we're just showing this in code. And now what we're going to do here is the part where we actually really send the kid off to boot camp to learn a bunch of stuff. And so this is where you're going to cue the montage music, and this kid is going to basically just start pounding math textbooks and teach themselves calculus and do all these other things. And so the num epochs parameter is another tuning parameter in this thing that it just takes experience to know. And so this is where data science looks kind of like an art instead of a science, because as the authors state from the TensorFlow doc, is that this is not something that necessarily, more is not necessarily always better. So there's like it will come from trial and error and just being empirical with your experiments to see what is the optimal number of epochs to train your model with before for it to provide you the best results. And we'll plot how the accuracy of our model has improved over time, which is pretty cool, because intuitively I think some people think, oh, if I just keep training it more and more and more, it should get better, right? But the answer is no. So there is some optimum here. And I guess the analogy here to extend it is like you stick a kid in too many days of math training boot camp, and they're going to burn out and they're going to hate math and they're going to suck on their math test. So that is potentially what's going on here with what we see. So that's how we do this, and you can read through these comments, but basically we're going to run this block, and this one does take the most amount of time, a whopping 3 seconds. But just look at how, for each consecutive 50 days of boot camp we put our kid through, their accuracy is improving and their loss is decreasing, and that's perfect. That's what we want to see. And so what we see here also, very interestingly, is that after day 150 the accuracy was, or at day 50 the accuracy was 99%, and then at day 200 the accuracy dropped to 97%. So it's like more training didn't necessarily mean better performance. And so again, that's the reason why this is an art as much as a science in terms of why, and these would be super complicated math problems to solve, but that's an important thing to note here. And then what we're going to do here is we're going to visualize all this stuff I'm talking about, and we're going to see it work. Your graphs might look slightly different too, because the first time I ran this, I will say it did look slightly different, but what we see is that it approaches it levels off, and so there's a lot of just trial and error with machine learning to arrive at models that are accurate for these data sets. But this is what we see, is that we're consistently missing fewer and fewer answers on our math exam, and so we're getting a higher and higher test score on our math test. And so now that we've looked at our training data set, like the math textbook we had those practice questions at the end of each chapter, so we've given this kid all those questions and they've gone to their math boot camp. But now it's time for the actual test day. When the kid goes to the classroom, it's 8 a.m. They're sitting down with their pencil, they have no idea what's about to come, and so we actually want to see how good of a job our kid is going to do on this math test with new numbers that it has never seen before. And so that's where we have a test data set. And so this is different. It is not the same, and there shouldn't be overlap between your test data set and your training data set, because as hopefully we know from our experience, if your test was exactly the same as your the practice questions you did for homework, it's a pretty easy test and you don't really learn much. Or you actually don't really get to see how well you can apply your knowledge to a different problem. Same thing with your test data sets, is that this is the opportunity for you to see how well your model will perform with data it's never seen before. And so this thing literally does the same thing we're doing in the beginning, just downloads that data set from Google. They provide this CSV. You guys can just click on this link too. It will literally just copy this to your you can click on this, it'll take you to your thing, and we've defined this in our memory or on our disk. And now what we're going to do is we're going to make use of TensorFlow's it's going to ingest that test CSV file that we've just given it and actually test the data set. So I'm going to go through that, and we're going to run this line, and we're going to see that our kid got a 96.667% on their math test, or in our case, in their botany test, to see how well they were able to answer questions about unknown types of iris flowers, which is pretty cool. So without knowing anything about, without having to manually do anything with determining averages or anything like that in terms of petal lengths, our machine learning has been able to determine this on its own. And again, we can see the raw test data. So like if you're like, oh, that's really great, I want to see your actual test, your math test, you can run this line right here. It literally tells you what the prediction was. So the prediction is what comes from your model, and y was the true value. And so you can see how well it is able to predict the true value based on something it's never seen before. So it's really cool to actually see this stuff, and it's working. And this final thing here literally just says the thing that I think is one of the most important things to come out of your model is the confidence intervals, as well as a guess as to what it is. And so what we've done here is we've essentially passed in 3 new math problems that this kid has never seen before, and we're asking it to tell us what is the answer. And we don't even know the answer, just because we don't know what label this is. And so what this is telling us is that with 98.6% confidence, based on these features of this flower, it has to be Iris setosa. And the same thing goes for versicolor, and virginica. So that is pretty cool. And so that is an introduction to machine learning. I know this was a long-winded video, but this is something I've spent a lot of time trying to learn myself, and I wanted to share it with you guys. And I really think this is some awesome stuff. I'm excited to see how people apply this to tons of new problems. If you have any questions or comments, love to hear them. And happy holidays, everyone. I'll talk to you guys next time.